Think you know your trees? Validate Binary Search Tree is a Pattern Mastery 100 essential and a classic filter in Google, Amazon, and Microsoft interviews. Nearly 1 in 3 candidates get tripped up by subtle edge cases or misuse of recursion. Master this, and you'll be ready for any problem that tests understanding of tree invariance and value constraints. Let's use the basic approach to tackle Validate Binary Search Tree so you'll never miss a hidden bug or boundary case. Let's break it down. Given the root of a binary tree, determine if it's a valid binary search tree, BST. For every node, all values in its left subtree must be less than the node's value, and all values in its right subtree must be greater than the node's value. Input: root node of a binary tree. Output: Boolean, true if the tree is a valid BST, otherwise false. Here is a real-world example. Suppose you're maintaining a database index tree. If the tree violates BST rules, searches become incorrect or inefficient. An interviewer might ask, how would you validate a config tree to ensure proper ordering for efficient range queries? Let's assess. What's tricky? A common mistake is to just compare each node with its immediate children, but BST rules require every value in the left subtree to be less than the current node, and every value in the right subtree to be greater, all the way down. Think step by step. Use recursion with value boundaries. Each time you descend left, update the upper bound, current node's value. Each time you descend right, update the lower bound. If any node violates these constraints, the tree isn't a BST. Let's go deeper. Start with a full possible value range. Example: from -infinity to +infinity. At every node, if the value isn't strictly within min, max, return false. Recursively validate left and right subtrees, passing updated bounds. Edge cases: duplicate values are not allowed in a BST, must be strictly less/greater. An empty tree is a valid BST. Subtle violations deep in the tree. Example is a right child of a left subtree is greater than root, must be caught. Here is the structure. Write a helper function with node, min, and max parameters. If node is null, return true. If node's value not in min, max, return false. Recursively validate left subtree, max equals node's value. Recursively validate right subtree, min equals node's value. Return true only if both subtrees are valid. Now let's implement the inorder traversal approach, verifying that the values appear in strictly increasing order to confirm BST validity. Here we begin by defining a class called solution. Think of it as a container that holds our algorithm. This line defines a function named as validBest that takes a tree's root node as input. This is the main function we'll call to check if the tree is a valid binary search tree. We create an empty list called stack. We'll use it to keep track of nodes as we explore the tree, like putting bookmarks while reading so we can come back later. This sets prev_val to -infinity. It acts as a baseline, the smallest possible value. So the first real node we read will always be bigger. This matters because BST values must always be increasing during an inorder traversal. We start our traversal at the root of the tree. This loop keeps running as long as there are nodes still to process or nodes stored in our stack. It ensures we visit every node once, which is why the time complexity is O(n). This inner loop walks all the way down the left side of the tree, just like following someone down a long hallway until it ends. We push the current node onto the stack so we can come back to it later. Think of it as placing a bookmark. When we reach the end of the left branch, we pop the top item from the stack. This is like opening the last bookmark we placed, returning to a previous node. This line checks the key BST condition. Every new value must be strictly greater than the previous value seen. If not, the BST rule is broken, so we immediately return false. If the rule is violated, we stop right away. The tree is not a valid BST. We update prev_val to the current node's value. This is like saying, okay, this value is now the new benchmark for the rest of the traversal. Next, we move to the node's right child, which in a BST contains larger values. The algorithm then repeats the same process. If we finish the entire traversal without breaking the BST rule, then everything was in strictly increasing order, meaning the tree is a valid BST. And that's how this algorithm works. It first uses a stack to simulate an inorder traversal setup, then checks values one by one to ensure they strictly increase. Efficient, simple, and elegant. Let's validate our BST using this input: 2, 1, 3. This represents a tree where 2 is the root, 1 is the left child, and 3 is the right child. In a valid binary search tree, if we perform an inorder traversal, left to root to right, the values should come out in strictly increasing order. Visit left subtree, then we get 1. Visit root, then we get 2. Visit right subtree, then we get 3. So the in-order sequence is 1, 2, 3. It's strictly increasing, with no duplicates and no violations of the BST rule. All left less than root less than right. That means the tree is a valid BST. And that's exactly what our function returns, true, matching the expected result. So, our implementation is correct. The in-order traversal check correctly identifies this tree as a valid BST. Now let's implement the recursion with bounds method, ensuring every node's value stays within its valid range as we traverse the tree. We begin by defining a class named solution. This class will hold our recursive BST checking method. This defines the main function as validBST, which takes the root of our tree. This is where our algorithm starts. We define a nested function called helper. Think of this as a specialist worker whose job is to check one part of the tree at a time. It receives node, the current spot we're inspecting. Low, the minimum value this node is allowed to have. High, the maximum value this node is allowed to have. If the node is empty, meaning we've reached past a leaf, that's perfectly fine. An empty subtree is always valid. We return true because reaching null means no BST rule was broken. Now we check the most important BST rule. Every node's value must fall strictly between low and high. This condition ensures that values remain ordered correctly across the entire tree, not just locally. If the node's value breaks that allowed range, the tree is not a valid BST, so we return false immediately. This is the heart of the recursion. We check both sides of the tree by shrinking the allowed boundaries. For the left child, the maximum allowed value becomes node.val. For the right child, the minimum allowed value becomes node.val. Think of it like giving each child its own stricter rulebook. Both sides must return true for the entire subtree to be valid. This recursive structure touches each node once, giving us O(n) time complexity. Finally, we call our helper function on the root node. We start with the widest possible boundaries, -infinity to +infinity, meaning the root can have any value. From there, the boundaries tighten as we go down the tree. And that's how this algorithm works. It first sets global lower and upper bounds for the root, then recursively tightens those bounds as it checks each subtree. Efficient, simple, and elegant. Now let's test the bounds-based recursive solution on this tree. 5, 1, 4, null, null, 3, 6. Here, 5 is the root, 1 is on the left, and 4 is on the right, with 3 and 6 as children under 4. The idea of the bounds approach is simple. Every node must lie within a valid range, min, max. For the left child, the max becomes the parent's value. For the right child, the min becomes the parent's value. Walking through. Start at 5 with bounds, -infinity, +infinity, that's valid. Go left to 1 with bounds, -infinity, 5, then 1 is valid. Go right to 4 with bounds, 5, +infinity, here's the problem. 4 is not greater than 5, so this already violates the BST rule for the right subtree. Even deeper, 3 is in the right subtree of 5 through 4, so it would also be constrained to be less than 5, but 3 is clearly less than 5. The structure doesn't satisfy the global BST property. And that's exactly what our function returns, false, which matches the expected result. So, our implementation is correct. The recursion with bounds method successfully catches the violation in the right subtree and correctly rejects this tree as an invalid BST. So, how do you really know if a tree is behaving like a proper binary search tree? Validate binary search tree is the perfect check of whether you understand how recursion and constraints flow through a tree's structure. Let's do a recap. The problem asks us to confirm if a given binary tree follows BST rules, meaning every node's left subtree has smaller values, and every right subtree has larger values. Conceptually, it's about keeping the entire structure ordered, not just comparing neighbors. We discussed how many people slip by only checking parent-child pairs. The trick is realizing that each subtree inherits boundaries from its ancestors. As we move down, we must update those value limits, shrinking the valid range for each recursive call. Our logic was simple but powerful. Start with a wide range, say from negative to +infinity. For each node, verify it fits within that range. Then, move left with an updated upper bound and move right with an updated lower bound. The recursion ends cleanly when all nodes fit their limits. We coded this recursive check, starting from the root and passing updated boundaries as we traversed. The function neatly returned true or false depending on whether every node respected its constraints. Running the solution on LeetCode confirmed it works perfectly. Valid BSTs passed as true. Invalid ones returned false, and tricky edge cases, like deep violations or empty trees, were all handled correctly without errors. The key takeaway: a valid BST isn't about direct neighbors, it's about inherited rules. Mastering that recursive boundary mindset ensures you won't miss hidden violations buried deep in the tree.